Lagrangian, which is a function of q dot p in general, and we have this principle that the action variation in the action for paths which slightly vary from the actual path while maintaining the endpoint fixed is going to be 0, and from that we have derived this set of equations. So these are called the Euler-Lagrange equations of motion, and you can write them down under certain conditions. The condition, of course, is that you should have an action in the first place, and more importantly, all the cues that you are using to describe the action, all the coordinates that you are using, they are actually independent. There may be some situations where you cannot avoid using dependent coordinates. Those are more advanced situations, something which you will be thankfully not subjected to in this class. But the basic idea, one thing you have to remember is you cannot write down these equations if your coordinates are dependent. That's one very important thing. You should be able to vary one coordinate without changing any other. That was part of this derivation. So this was what we had done before, and we had also said that the most common form, although not the general form, most common form of the Lagrangian, especially if you want to reproduce point particle mechanics, is of this form: kinetic energy minus potential energy, and typically, this is typically, not always, typically, so even within this being the most common form, even there, typically, G is something which depends only on position, length of Q dots, right? V depends only on the Q's and not on Q dots. Again, typically, not always. And T depends on Q dots and Q's very often, depending on which kind of coordinates you are using. But Q dots quadratically. Okay, that's something which you all are familiar with. All the kinetic energies that you have seen so far basically are half mass velocity square. So you would expect that the kinetic energy would in general be could depend on coordinates because of some change of coordinates. For example, in our example with polar coordinates, L worked out to be, this is an example of course, not the general case, half m r dot square plus r squared theta dot square. This is the kinetic energy part minus the potential energy part, which could depend on both r and theta, but typically again it does not depend on r dot and theta dot. It depends on r and theta. And you can see that the kinetic energy part here, again this is typical, not always but in most cases, is quadratic in the velocities. Okay. The velocities r dot and theta dot occur in power 2. Well, quadratic would also mean r dot times theta dot. That's also quadratic. Right? 1 power each would also make 2 powers. Here you do not have terms like alpha into r dot or beta into theta dot. There is linear terms, and you definitely would very rarely find higher order powers, say r dot cube or r to the 4 and so on. Again, such things happen sometimes, depending on your system, but very, very rarely. Yeah.
Like you said, this happens typically.
Yeah.
So for the other cases, does the Euler-Lagrange thing?
The Euler-Lagrange thing still works. That this equation works simply based on the fact that you have this action principle. Okay, and the Lagrangian that you use has to be tailor-made to fit your system. Okay. So the most common form of the Lagrangian, the one that you will use most often, at least when you are dealing with point particles and their mechanics, is T minus V. Okay, and in that, in almost all situations, but there are important exceptions where V does not depend on the velocities, depends only on position. T depends on Q dot quadratically. That's the most common situation, not the situation which happens everywhere. In one very important exception, although it's slightly different from this, one very important exception is charge in an EM field. Now there of course you have a force which depends on the velocity, and it's easy to see that you cannot reproduce that with a potential energy which does not depend on the velocity. After all, the force, the standard for the force to potential energy relation is minus gradient of the velocity, right? And if the velocity depends only on position, and you take its gradient, of course you are going to end up with a force which depends only on position. So velocity dependent forces, an example of which is the Lorentz force in an electromagnetic field, or a charge in an electromagnetic field, cannot be written down using a potential which is independent of Q dot. It can actually be written down using a potential which depends on Q dot. Okay, so, and you usually don't call that a potential, and you don't write it V, you write it U. That's true. And perhaps even T. So, we are not going to cover this in this course. After all, we don't have the time at all to do that. But in third year, you will learn about this. That is, how to use velocity-dependent potentials to describe things like velocity-dependent forces.
So, what is it called actually? EM field, like what is that potential called? Like, is there?
It's called a velocity-dependent. It's called the Lorentz field potential or EM potential. It's not even called a potential. It's called a generalized potential. Potential we usually use. By the way, although strictly speaking, we keep on saying potential, we really mean the potential energy. It's charge times that. And this is actually one important exception. There's a very important exception to this, a very common and very important system. That's why I'm mentioning this. Although we will deal essentially with these situations, but this does happen. And in other situations, where the second thing fails, T depends on Q dot quadratically, one very important place where this fails is in non-inertial frames. You can still use the Lagrangian formulation, but then you will find that if you try to use, there the kinetic energy and the potential energy will be calculated in an inertial frame, but then you can always use the coordinates of the inertial frame and rewrite them in terms of coordinates of the non-inertial frame. So you can write a Lagrangian which involves coordinates as measured from the non-inertial frame. And there, if you did that, one very common thing that happens is kinetic energy ceases to be quadratic in Q dot, also as linear terms and constant terms. Okay? That's very easy to understand. But I will give this as an assignment to work out that if you did a very simple coordinate transformation, what happens to this when you are dealing with a time-dependent accelerated observer? Okay. But those are exceptions, we are not going to deal with them. I am just mentioning that you should not expect to get this everywhere. Okay?
Sir,
Yeah.
is it possible to L not equals to a T minus?
Of course. After all, it is not T minus V even for the first exception. There is no V. Or there is a V, which is the electrostatic potential. And that alone, of course, does not describe the electromagnetic force. You need the magnetic field.
Yes.
Right? In many situations, it's not. But the common situation when you are using point particle mechanics, it is T minus V, and that's the one we are going to stick with in this class.
So can you please explain that non-inertial frame part?
No, all I am saying is you can also use Lagrangian dynamics in a non-inertial frame. But if you did that, you would typically not get a quadratic kinetic energy. You will also have additional pieces.
Quadratic dependence of Q.
Purely quadratic dependence on Q.
Oh.
Yeah.
So, what is the significance of physical significance of extreme coefficient, and why do we use it?
First of all, the physical significance is that it works. There is no meaning to the word physical significance. Okay. If something works in physics, it's physically significant. That's a rather non-glamorous thing to say, but that's what it really is.
Why does it work?
Why does it work? Because we essentially manage. Okay, there's a very deep reason why it works. Unfortunately, we cannot tell you what the deep reason is because we'll have to learn a lot more. You know, there is one very obvious reason why it works. There's a quantum mechanical reason why it has to work. It follows from quantum mechanics. I can explain that outside the class, not in the class. Yeah. So because charge, when a charge is in an electromagnetic field, the force it experiences depends on the velocity, right? And the velocity dependent force cannot come out of a potential which does not depend on velocity. If a potential depended only on the velocity and we took its gradient, no matter how complicated the potential is, the result will be something which is a function of position. Right? You cannot get V out of somewhere where there is no V to begin with. So the fact that the electromagnetic field produces a force on a charge which depends on the charge's velocity, that cannot be reproduced by a V which is independent of the position of the velocity. Right? It turns out that you can write down a function U, again, will be a part of the assignment, but not essential for this course. Because will be, so in the next assignment sheet, there will be optional assignments which can try to understand these issues, but they will not be part of something you have to absolutely learn for the exam. Okay, but there will also be other assignments which you should learn up for the exam. So you should focus on them first. Unfortunately, if I had 2 more classes, I would have done a better job of that, but I don't, so I can't really do much more. Now, some terminology. Del Qi dot. Q's are called generalized coordinates, Q dots are called generalized velocities. And del Qi dot, these quantities, they have a name which is borrowed from the fact that if you had L, say one-dimensional L, which we had already shown the other day, there del L del X dot is simply mx dot, right? And that's a very well-known quantity. What is mx dot? Momentum. The x component of the momentum, or the only component of the momentum in one dimension. If it had been 3-dimensional problem with Cartesian coordinates, half mx dot square plus half my dot square plus half mz square, minus capital V of x, y, z. Del L del x dot will be mx dot, del L del y dot will be my dot, and so on. So at least in those cases, these derivatives it seems like a hurricane from a immediate Fermi wave. Okay. So this is what, in general, will be called a generalized momentum. So when you take the generalized velocity and differentiate L with respect to that, what you get is the ith generalized momentum. So in this case, for example, for this Lagrangian, you have 2 generalized momenta. There are 2 degrees of freedom. You can call them 1 and 2, or you can call them R and theta, just to indicate that they are different. PR would be mr dot. Note that this looks very much like mass into velocity, but r dot is not the velocity component in the radial direction, right? You already know that the velocity component in the radial direction has 2 pieces. Not only r dot is only one part of it, right? Is that okay? So, really, everybody agrees. Why does everybody agree?
So what do you say?
First lesson is you should never agree to something just because it's being said confidently. What I said just now term is completely wrong. Even in radial coordinates, the radial velocity component is r dot. There is no additional term. There is an additional term in the acceleration. The acceleration is not r double dot. So, here at least, this sort of looks like the velocity momentum component that we knew in the radial direction. This one, whatever it is definitely not standard momentum. Can't be because it has the wrong dimension in it. Right? M r square theta dot. M times r theta dot would be mass times tangential velocity. This is r times that. Right?
This angular momentum.
Selfie time is over, right? Then why are you sitting there? There are chairs here. There are empty chairs here. Why do you have to sit there? Is that you can't see from there, you can always come forward. Which P? PI. The IFP is PI is del L del Q dot I. Oh, is this big enough for the back of the class? In case you are interested in looking at it? Okay, that looks like a thumbs up, which I interpreted as positive, because remember in Indian tradition this is also called a thinga, right? Anyway, let's come back to this. One immediate thing which happens. So we have some terminology down. One is generalized coordinate, generalized velocity, and now we have generalized momentum. Now one immediate thing that you can see from here, from the equations of motion, is, you can of course rewrite those equations of motion as dp I dt. Right? That's what this ddt of del L del Q dot I is equal to del L del Qi. This is the same as the Euler-Lagrange equations of motion. I've just changed the nomenclature a bit. Okay? But what this tells you is something rather stunning. It tells you that if the Lagrangian does not contain a particular coordinate explicitly. Okay, now you might say, why would that happen? Let's take a look at a specific example. Polar coordinates in 2 dimensions. Let's use this to understand something like minus g capital M small m over r. That's the potential energy of a point particle of mass small m moving in the gravitational field of a very heavy particle of mass capital M. Right? So here the heavy particle is assumed to be stationary, it's not moving, so we are not worrying about its kinetic energy. Okay? So that of course is not really true about our solar system, but almost true. You can ignore the motion of the sun at least in the first approximation. So this makes it a problem where the potential energy term has R but does not have theta. Okay. And that also tells you that the force that acts on this particle is always radial. It has a radial component only. Or central. That's what we usually say. It's always directed towards the center. Okay. In fact, not only gravitation, any central potential would give you a V which depends only on R and not on theta. Okay? Now, we can look at this scenario. Here, what are your generalized coordinates? R and theta. Generalized velocities, R dot and theta dot. Right? The Lagrangian typically is expected to be a function of R, R dot, theta, theta dot and T. That's the most general possibility. Here you can see, you had already seen that there was no T in what we had to do, right? So T is a possibility, but T doesn't have to be there. Notice that here, R dot is there, theta dot is there. R is there in the Lagrangian both here and here. But theta is missing from the Lagrangian. Okay. Right? Now theta missing from the Lagrangian essentially means that you can change theta without changing the Lagrangian. Okay, and since the Lagrangian is what essentially talks about the dynamics and gives you what the equations of motion etc. are, it essentially means that changing theta will not change. Suppose you did a did something. So you made somebody shut their eye and change the theta in between for this particle. The dynamics will progress just as before. So why is that true? That's because you have a rotational symmetry here. This system has there in the radial direction, of course, there's a particle sitting here, and the distance from that center matters, but the angle doesn't matter.
So the particle is moving in circular.
No, it's not moving in a circular. It's moving under whatever force. Even for a particular look, you should be able to distinguish between what happens for a particular motion or what happens for the law of force. If you change the angle, would the force change? Keep R the same, change the angle. The force will change only, force will only turn around also. Force of course will change. If the particle is here, the force will be in this direction. If the particle is here, the force will be in this direction. But if you have rotated the thing, then this direction is what becomes this direction, right? So before and after you rotate, you will not be able to tell the difference. It will still be the same equation of motion. And that is what you mean when you say that there is a symmetry here. A symmetry essentially gives the easiest way of recognizing a symmetry is if your Lagrangian doesn't contain a particular coordinate, then you can change the coordinate without, and leave the others unchanged, but you just change that coordinate. In this case, change theta without changing r. Nothing changes. Okay? So, one very important reason why Lagrangian method is favored over say Newtonian in advanced calculation is that it helps us to deal with symmetries much more effectively. It gives us a very good way of identifying the symmetries, also handling them.
Sir,
Yeah.
so you said we are changing the direction. So theta, we are giving.
So suppose I had this system where the particle was moving around. Okay. Somebody does an experiment, figures out what the laws of force, etc. are. Okay. Now I ask you to go out of the room and then suddenly increase the R. Use the motion. You will be able to come in and tell me that something has changed drastically. Okay. If I were to change the theta and not the R, the particle will still be going around in the same orbit as before. Just it turned one. Okay. And from that you will not be able to say that something drastic has happened. Okay. Do you understand the point? Since the angle has also been changed, when you come in and look at the change direction as the original direction, so you don't see anything different. But even if you had looked at the same direction, you would see an enlarged R. The motion will be slower and will take more time, for example, and so on.
But then we are changing the theta, right?
So scaling R without changing theta is not a symmetry. Which you can see here because R appears in the Lagrangian. Changing R will change the Lagrangian. Keeping the R same, just changing theta does not change the Lagrangian. It does not change anything about the equation.
But if we are considering the equation there, the theta dot, which is there.
So theta dot is not changing. Right? Theta is what we are changing. Once again, theta and theta dot are independent. R, theta, R dot, theta dot, these are independent variables. These are all numbers, by the way. Value of R is being changed, not R of theta. Or value of theta is being changed. Okay. So one important thing is what happens is if you have symmetries, you almost always, not always again, but one of the most easiest ways of seeing that there is symmetry is you have something which is called a cyclic coordinate. What is a cyclic coordinate? Is simply a coordinate which is there in the problem but which does not appear in the Lagrangian. In this example, R is not cyclic, right? But theta is. Theta does not appear in the Lagrangian. Okay. The name cyclic is something you borrow basically from the fact that very often cyclic coordinates are basically angles, like theta in this case. So that it goes round in a cycle and comes back again. Remember, when you go all the way down, the angle value comes back to its original value, right? That kind of behavior is what gave it this name because most common examples happen to be angles, but doesn't have to be. Any variable which is not present in the Lagrangian is a cyclic coordinate. Of course, if the coordinate is not present in the Lagrangian, neither is the velocity, then you might just as well forget about it. That is not in the problem at all. In this case, why are we worried about theta? Because theta naught is there in the Lagrangian. If theta naught also had been absent from the Lagrangian, then theta would not have been a problem, have been something to deal with in this problem at all. Now, one immediate consequence of this would be if Qi is cyclic, and that simply means Lagrangian doesn't explicitly contain Qi. What happens to the right hand side of that equation that I've written down? F0, right? That 0 doesn't tell you that the Lagrangian is constant or anything. It just tells you it does not depend on the ith coordinate. That's it. Okay, it depends on the other coordinates. However, what is the left hand side then? dpi dt, that's a total time derivative, how it changes with time. So when Qi is cyclic, dpi dt is 0. And that means Ti is conserved, it does not change with time. Okay?
Sir,
Yeah.
it doesn't depend on Qi as a value, but it does depend on Qi as a function of time, right?
Yeah, because it depends on Qi dot.
Yeah, yes, sir, that's what I meant. Like, very fine.
You were talking about changing timing. So, like when we are changing the
Okay, for the time being, let's not get too much into changing theta and symmetry because that's something that will take way too long. Okay, sorry, I don't have the time. Let me just put it this way, the simplest way to spot the cyclic coordinate, that's what is going to serve you well in the immediate future, which is exams of course, is that, I'm sorry, I shouldn't really do this, but I don't have the time to give an elaborate explanation right now. Is to just see whether that particular coordinate is there in the Lagrangian or not. Here theta is not in the Lagrangian, R is. Right? R is there in G of R, it's also there in the kinetic energy. But R is. That's important, so R is not cyclic. Theta is cyclic. And theta being cyclic means theta is a conserved quantity. So the reason why I brought up symmetries is the following, one of the most important results in physics, all of physics, and specifically mechanics, happens with something called Noether's theorem. Emma Noether was one of the greatest mathematician physicists of all time, who wasn't really celebrated that much during her lifetime for the simple reason that she was a woman in a male-dominated society. But she gave us one of the most important results in all of physics, which is symmetries have conservation laws along with it. If you have a symmetry, you would typically have a conservation law. Okay. Not always again, but there are conditions, but those conditions can be left for a higher class.
The argument of why Qi is
Well, if Qi is cyclic, that simply means there is no Qi in the Lagrangian. So if you do del Qi, you are going to get 0, right? If a particular variable is not present in your function and you differentiate with respect to that partial, you are going to get 0 simply because if you change Qi and Qi alone, L is not going to change, right? Del Qi measures just that. If you change Qi and Qi alone, how much does L change? If L does not contain Qi, in this particular example, L does not contain theta, then del theta vanishes. But the Euler-Lagrange equation of motion tells you that dpi dt would then be 0. So pi would be conserved quantity. Okay. So this is a very important result. Of course, this is not the full impact of Noether's theorem. It's a much more complicated and rich theorem. It tells a lot more than just this. But I will need this thing. Let's use this power. Yeah. So if you have cyclic coordinates, you can immediately get conserved quantity. Yeah. P theta, which is the generalized momentum corresponding to theta, that's conserved. That actually happens to be the angular momentum in this case. Then Px would be conserved. Wait a minute, we are going to come to that. Because that's my next one. Okay, let me just get rid of some more on the board. So one very important quantity or one very important result that we have seen right now is that if you have symmetries like rotational symmetry, change theta, Lagrangian doesn't change. In 3 dimensions, it could be change phi, Lagrangian doesn't change, right? If that happens, in 3 dimensions, for example, the Lagrangian would be half m, even for a free particle, no potential energy. R dot is the velocity component in the radial direction. What is the velocity component in the theta direction? Spherical polar coordinates, R dot means you are changing R, theta changing theta phi. You're moving straight that way. That's the velocity component. If you change theta and theta alone, what happens? This angle changes, so you come down. But that's a displacement of radius times theta dot, right? You're moving in a circle of radius r. So you have a r theta dot, that's the velocity component, which is, this is also there before in 2 dimensions, but now it's also there because this is different theta. But what about phi? If you change phi, you move in a circle whose radius is not r, whose radius is r sine theta, this radius. And you move in a circle like this. So you get r square sine square theta phi dot square. Of course, if this were not a free particle, the Lagrangian would have more than the kinetic energy, it would also have potential energy. But notice one thing, that even for the free particle, in 3 dimensions, R is not cyclic, because R is there in the kinetic energy. Not R dot, R itself is there, R square, theta dot square. R square sine square theta phi dot square. Theta is also not cyclic, right? There is a sine square theta. Phi is cyclic. Of course, phi may or may not be cyclic overall because it will depend on the potential. For a central problem, V depends only on R, then phi is cyclic. Even if V depended on R and theta both, even then phi will be cyclic. Of course, if V explicitly dependent on R, theta and phi, that is had a phi dependent, then of course, if phi would not be cyclic and P phi would not be conserved. But otherwise, P phi would be conserved. Now, quick next topic, which is, for some reason, which I am not going to disclose right now, but you will soon see, I will consider a quantity like this. So I take the ith momentum, take the ith velocity, multiply the two together. Now when you multiply momentum by velocity, the quantity that you get, what is the dimension of that quantity?
Energy.
Well, you have to remember that that's true only if you are using standard momentum, standard velocity. Is it also true when you are using generalized momentum, generalized velocity? Well, Pi is, you know what Pi is? General, then Q dot I, right? So dimension of Pi is the dimension of the Lagrangian divided by the dimension of the velocity. Dimension, also the differentiation is not a division. Dimensionally it is, right? And then when you multiply it back by the velocity, you get Lagrangian's dimension. Lagrangian happens to be the same dimension as energy. After all, this kinetic minus potential is the most common case. So this is something the dimension of the Lagrangian. And from this, let's just subtract the Lagrangian. Okay. Now this quantity, what will this be a function of? What was L a function of? Q dot and T in general? Forget about cyclic coordinates and all that. We are back to general case here. L is a function of Q dot and T. Q dot of course is a function of Q dot. It is Q dot itself. What about P? P depends only on the generalized coordinates.
Say QI also. QI.
P depends on, P in principle depends on all the Q's, all the Q dots. In principle, specific examples may be different. You are taking a function of Q dot T, differentiating that with respect to Q dot I. The resulting thing will be a function of all Q's, all Q dots, all T, and not only one T.
Yes.
Of course, in a special example, there may or may not be a T dependence, there may or may not be a Q dependence, and so on. So this thing, small h, is a function of Q dot T. When I write this, I mean all the Q's, all the Q dots, all the T's. Well, only one. Okay? Right? So why are we looking at this function? Let me just give it a name first. The name may not sound like much right now. Okay, the name is often called the Jacobi integral of motion. Jacobi may not be somebody who is very familiar to you right now, although you know of something about which bears his name. The Jacobian. The Jacobian is of course named as the same Jacobi. And Jacobi was a very eminent mathematician who did a lot of stuff. Okay. So, but why are we looking at this? To see that, let's look at this derivative. What is this going to be? Sum over I. Actually, I could use an upstairs downstairs summation like we did in special relativity, and in fact, it is what is done in advanced mathematics. For the time being, I am writing the explicit stuff. I equal to 1 to m. What will this be? Pi qi double dot, right? Differentiate qi once, then you differentiate once again. Plus sum over I pi dot qi dot. I hope the dots are visible. Now, minus Lagrangian. Lagrangian's time derivative. But Lagrangian, why does it depend on time? Depends on time because it may have an explicit time dependence. But it may also depend on time through the fact that it depends on q, and q depends on time. Q dots also depend on time, right? Remember, this is ddt that we are doing. So, all dependence have to be taken into account. In fact, you get something like this. Lagrangian depends on the IHQ, but you want ddt, not del del q. So multiply this by dqi, not del qi, dqi. So qi dot. Okay? Right? But that's not all. So Lagrangian also depends on the n q dots. Right? So plus del n q dot I q double dot I. Right? This is the ddt of q dot. Now the bracket closes here simply because I don't want to put the other term in this sum because there's only one of them. Only one t. Minus del del t. So L depends on q dot and t. So when you talk of dl dt, you will figure out how fast it changes because q is changing. All the n q's, which is why you have sum over the n q's. How the q dots are changing, and of course if t changes, there's a del del term which comes in because L explicitly depends on t sometimes, not all. But now notice what happens here. Okay. Focus on these two terms that q dot. Okay, there are n terms here, n terms here. And can you see something about the coefficient? This coefficient is pi.
Sir,
This coefficient?
This is also.
Okay.
sir, that's q
Oh,
double
it's not
dot.
even the right term. This is double dot. I couldn't see the term myself. So, okay. Let's look at this term first. Qi double dot. We compare it with this one. Okay. But pi is del del qi dot, right? And there's a minus sign, so these two terms cancel out. What are the terms with the qi dot? Is pi dot and is dpi dt. But that, according to Euler-Lagrange equation of motion, is del del qi, right? The equation on top. So this term and this term cancels. So almost everything cancels. You will find the time derivative of h, and you end up with this very important result. That okay, rate at which h changes with time as the motion progresses is minus del L del T. And why is that a nice thing? Because very often the Lagrangian does not have an explicit time dependence, which happens when you have a symmetry. You change the time origin. You change when you set your clock, which is something we have been talking a lot about in STR, but you can of course set your clock in ordinary life as well. If you change the time at which you set your clock, what happens? The key variable shifts. But if your Lagrangian doesn't have a key in it, it doesn't change. Okay. Time translation invariance, another symmetry, would tell you would give you, this is 0, okay. So Jacobi function is conserved, Jacobi integral of motion or Jacobi function, whatever you call it, is conserved if there is no t in the Lagrangian, which is pretty common. All the examples that we have written down are examples where there was no t in the Lagrangian. Okay. There was t dependent in the Lagrangian through the fact that q and q dot as the motion progress depends on t. But as a function, these Lagrangians, the ones we wrote down at least, had no t in them. All of them has del L del T equals 0, and for them dh dt is 0. So Hamilton, this h, small h, the Jacobi function, will not change with time as the motion progresses. Yeah.
So can you give an instance where it is a function of not q and qi as a function of t, but it is explicitly a function?
Well, suppose you had suppose you had an electric field from outside which was changing with time. Say an electron in that pure electric field, the electric field is changing in time. They will be dependent. Or in the electromagnetic field, the electric field and magnetic field will both depend on time. So,
In that case, h will not be known.
in those cases, small h will not be done. Yeah. You have to be louder. And the rest of you, please. Then it does not conserve small h. Can't be conserved. First of all, conservative systems have capital L equals T minus V. Right? But T and V are typically both independent types. That's not always the situation. You may even have conservative systems which, if you are looking at from, say, an accelerated frame, for example, then L will have a time dependence, and L will not lead to a small h which is conserved. Okay, but that's simply, in that case, it would simply be because you are looking at this from an non-inertial frame. But you can use non-inertial frames just as well as inertial ones. That's one of the major advantages of using the Lagrangian formulation. You are not stuck to inertial frames only. Now, the important point is, why am I so excited with h being conserved? The answer to that lies in these two positions. This is the most typical situation, right? In the most typical situation, V is independent of the Q dots. So when you do Pi to form del L del Q dot I, you are actually just differentiating the kinetic energy. Right? You are not differentiating the potential energy because the potential energy does not have Q dots in it. Okay? And now, if potential energy is the pure quadratic in the Q dot, what does that really mean? Sorry, not the potential energy, the kinetic energy. The differential is just the kinetic energy, and the kinetic energy typically again is purely quadratic in the Q dots. What that means is the following. If you, potential energy of course depends on the Q's in general, also on Q dots, and typically not on time. Okay. So what will happen is you would have Q dot 1 up to Q dot n. Now when it's quadratic in Q dots, what that means is the following. If you were to double say all the Q dots, all of them, then what would happen to the kinetic energy? It will become 4 times. If you multiplied all the Q dots by some number, let's say lambda, what will happen to the kinetic energy?
Lambda square.
It will become lambda square times what it was, right? So if I did this, right, keep all the Q's the same, because you are not guaranteed that these are homogeneous quadratic in the Q's, but they are homogeneous quadratic in the Q dots, and multiply each of the Q dots by the same factor lambda, you are going to get 6.
So can you repeat that part again?
That's what quadratic dependence means. You change all the Q dots to lambda Q dots, the overall function picks up a lambda star.
So like what is homogeneously quadratic?
Homogeneous means exactly that. All of them have only quadratic terms. So for example, if you had Q dot square plus Q dot plus some constant, Q dot square would be a quadratic, Q dot would be linear, the constant would be order 0.
Right.
So that's not a homogeneous quadratic. Homogeneous quadratic only is quadratic term, like Q1 dot square plus Q2 dot square plus Q1 dot Q2 dot.
Oh, watch.
But you cannot have a Q1 dot term like that.
Each term has same power.
Each term has a power which adds up to 2.
So why are we changing QY dot?
Oh, because that's just, why are we doing that? You will soon see.
No T there.
Hmm?
All time. It's not dependent on time.
We are ignoring time dependence right now. We are only going to talk about situations where Lagrangian does not depend on time. If the kinetically depend on time, there's very little that can happen if you make the Lagrangian independent. Because we are interested in the situation where L does not have T in it, so that H is a conserved quantity, small h is a conserved quantity. Now, why did I do this? No reason except to say that this is what this statement means. Okay, I should have actually said purely quadratical. But an immediate, I don't know whether you already know this result, because somewhere in your maths class, somewhere down the line this result would have been taught, but may not have been. So this formula that you have, homogeneous functions you have already dealt with, right? Differential equations, solving them, homogeneous differential equations, so on, you must have dealt with this somewhere. But have you also studied Euler's formula for homogeneous functions? I don't think you have, but you may not have, or you may have. Anyway, let's look at what happens when you differentiate both sides with a sort of lambda. If you did that, what do we look at? Well, what we look at on the right hand side, that's easy. On the right hand side, you can easily see where there is lambda, right? Lambda is only here. There is no lambda inside that. So right hand side will simply give you 2 lambda times t, q1 to qn, q1 dot to qn dot, right? That's what your right hand side is. What about the left hand side? Here, there is no explicit lambda outside, the lambda is only inside. Each of these velocity components have been multiplied by lambda. So, it's actually going to be if you differentiate this with lambda, what will you get? The ith velocity you are differentiating with respect to, but the ith velocity is now lambda qy dot. So you have to differentiate that with respect to lambda further.
So what actually lambda is?
Anything, any number.
It is constant.
If it's a constant, I have to differentiate it. Lambda is just a value, just whatever you want, 2, 2.5, 1.7, any number will do. So del T del Q dot I is what you would get, but that's not the end of it. What is this? Is the ith velocity, but the ith velocity in this function, is it lambda? Is not, right? It's lambda q dot I. You are differentiating with respect to lambda. So what do you get here? Into ddt of lambda q dot I, dt lambda of lambda q dot I. That's a simple q dot I. Some lower. But evaluated at this point.
So dd lambda is dot. dd lambda is dot.
Huh?
You're writing dd lambda.
dd, yeah, I'm doing dd lambda both sides.
Okay.
How did I do dt before? The q dots depended on t, that's why I took a q double dot. Here lambda qi dot depends on lambda. What's its derivative with respect to lambda? Simply qi dot.
Sir,
Yeah.
so in the right hand side, you should also differentiate, I mean, with respect to
This side. Yeah.
So you should also have some term like that, because you differentiate with respect to lambda at first and then.
Wait a minute. Where is the lambda here on the right hand side? Maths is easy. You don't need to complicate it. You just find where the lambdas are, you differentiate it. Okay? What should have happened is not the key situation. What is there? You just look at what is there. Now, delta del qi dot. What is that? That's pi. Right? So this is the sum of pi qi dot. Not really. Why? Because the right hand side is being calculated not as q1, q2, qn, q1 dot, q2 dot, qn dot. It's being calculated with the arguments as q1, q2, qn, lambda q1 dot, lambda q2 dot, lambda qn dot. So this is really not pi. Pi is delta del qi dot calculated with the values of the arguments of q1, q2, qn, q1 dot, q2 dot, qn dot. Okay? Right? Delta del qi dot would not be pi qi dot, but we would love it to be. But when is this equal to pi qi dot? Well, I just told you when it is pi qi dot. When this thing is being evaluated at q and q dot, and not q and lambda q dot. Just put lambda equal to 1. After you differentiate, if you just put lambda equal to 1, delta del qi dot becomes pi. So what you get is sum of pi qi dot, this sum. In the most common scenario, not always the case, but in the most common scenario where kinetic energy is purely quadratic in the velocities, this simply becomes twice t. That equation told you is twice lambda times t, but that's true only when that's pi qi dot only when lambda is 1. So 2t. So now we have already shown that this is a conserved quantity if L does not explicitly depend on time. And small h, in the most common situation, and now you should recognize why you were making such a noise about it. In the most common situation, is kinetic plus potential, and this would become the statement about the law of conservation of energy. Okay? Clear? If the Lagrangian does not explicitly depend on time, the Jacobi function is conserved. The Jacobi function is a general function, but in the special situation, the most common situation we have, it is actually kinetic plus potential. Okay. Now, since I have run out of time, I am not going to talk about the next very important topic, extremely important topic, to the whole class. So this is where the syllabus ends. And it's all when I say syllabus, not the syllabus, of course syllabus doesn't end here. The syllabus has the Hamiltonian. So anybody interested in learning about the Hamiltonian in half an hour, stick around. Not interested in learning about it, or not interested simply because it will not be in the exam, you can just move out in a couple of minutes. Yeah. Yeah, in a couple of minutes, because I will introduce you. Hold on, let the people who want. Nobody wants to leave. I'm not going to penalize anybody who wants to leave. I will be happy if somebody is there. Now, if everybody stays in the class, then it will be in the exam.
बैग है पीछे मेरा बैग पीछे ब्लू कलर का পেছনে আছে দেখ পেছনে আরে নিচে